Have you ever looked up at the night sky and wondered about the stars? How did they get there? Where did the universe itself come from? We are about to embark on a cosmic adventure to explore the Big Bang Theory. This theory offers our best explanation for the origin and evolution of our universe. This is where our journey begins. Get ready to explore the wonders of the Big Bang. Our adventure awaits. The Big Bang wasn't an explosion in space. Instead, it was the expansion of space itself. Imagine a tiny balloon with dots drawn on it. As you inflate the balloon, the dots move farther apart. Similarly, the Big Bang involved the expansion of space. In the beginning, the universe was incredibly hot and dense. It was so dense, all of space could fit inside something smaller than an atom. This tiny point, called a singularity, contained all the matter and energy. As the universe expanded, it cooled down. This cooling process allowed particles to form, leading to atoms, stars, and galaxies. Imagine a faint afterglow of the Big Bang, a whisper of light that has traveled across the universe for billions of years. This afterglow exists, and it's called the Cosmic Microwave Background, CMB radiation. It's one of the most important pieces of evidence supporting the Big Bang Theory. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Before this, the universe was a hot soup of protons and electrons, preventing light from traveling freely. When atoms formed, light was finally able to stream across the universe. Today, we observe this ancient light as the CMB. It's like a baby picture of the universe, showing us what it looked like in its infancy. The CMB is incredibly uniform, meaning it has almost the same temperature in every direction we look. This uniformity provides strong evidence for the Big Bang. It suggests that the early universe was incredibly homogeneous, meaning it was very similar throughout. The CMB is a treasure trove of information about the early universe. By studying its subtle variations, scientists can learn about the universe's age, composition, and even its geometry. Another crucial piece of evidence for the Big Bang comes from the observation of distant galaxies. When we look at these galaxies, we notice something peculiar. Their light is stretched, shifting towards the red end of the electromagnetic spectrum. This phenomenon is called redshift. Imagine the sound of a car engine. As the car moves away from you, the sound waves stretch out, making the pitch lower. Similarly, as light from distant galaxies travels through expanding space, its wavelengths get stretched, making it appear redder. The farther away a galaxy is, the faster it appears to be moving away from us, and the greater its redshift. This observation, known as Hubble's law, strongly supports the idea that the universe is expanding. Redshift measurements provide compelling evidence that the universe is not static but rather dynamic and expanding. This expansion suggests that the universe was once much smaller and denser, just as the Big Bang Theory predicts. Section 5. The abundance of light elements, another clue. The Big Bang Theory also explains the abundance of light elements in the universe. These elements, such as hydrogen and helium, were created in the first few minutes after the Big Bang during a process called Big Bang nucleosynthesis. As the universe expanded and cooled, protons and neutrons combined to form these light atomic nuclei. The theory predicts the relative amounts of hydrogen and helium that should have been produced, and these predictions match observations remarkably well. The abundance of light elements in the universe provides further support for the Big Bang Theory. It tells us that the conditions in the early universe were just right for the formation of these elements in the observed proportions. Section 6. From particles to atoms, building blocks of the universe. In the first fraction of a second after the Big Bang, the universe was an incredibly energetic and chaotic place. As the universe cooled, this energy began to condense into tiny particles, the building blocks of all matter. These particles included quarks, electrons, and other fundamental particles. As the universe continued to cool, quarks combined to form protons and neutrons, the particles found in the nucleus of an atom. However, it took another 380,000 years for the universe to cool enough for electrons to be captured by these nuclei, forming the first atoms. This era, known as recombination, marked a crucial turning point in the universe's history. Before recombination, the universe was opaque, with light constantly scattering off free electrons. After recombination, the universe became transparent, allowing light to travel freely. This transition from a hot, opaque soup to a cooler, transparent universe paved the way for the formation of the structures we observe today: stars, galaxies, and ultimately planets like our own. Section 7, the first stars ignite, a universe illuminated. After recombination, the universe entered a period known as the Cosmic Dark Ages. During this time, the universe was filled with vast clouds of hydrogen and helium gas, but no stars had yet formed. Gravity slowly began to pull these clouds together, creating regions of higher density. As these regions collapsed, they heated up, eventually reaching temperatures and pressures high enough to ignite nuclear fusion in their cores. This marked the birth of the first stars, colossal balls of hydrogen and helium that flooded the universe with light and heat. These first stars were very different from the stars we see today. They were much more massive and short-lived, quickly exhausting their nuclear fuel and exploding as supernovae. These supernovae explosions enriched the surrounding gas with heavier elements, paving the way for the formation of more chemically complex stars and galaxies. The first stars marked the end of the cosmic dark ages and ushered in a new era in the universe's evolution, one characterized by the formation of increasingly complex structures. Section 8, galaxies emerge, islands in the cosmic ocean. As stars continued to form and evolve, gravity continued to shape the universe on even grander scales. Over millions and billions of years, stars clustered together, forming vast collections of stars, gas, and dust held together by their own gravity, galaxies. Galaxies come in a variety of shapes and sizes, from majestic spiral galaxies like our own Milky Way to giant elliptical galaxies containing trillions of stars. The formation and evolution of galaxies are complex processes driven by gravity, star formation, and the interactions between galaxies. Galaxies are not randomly scattered throughout the universe. They are often found in groups and clusters, bound together by gravity. These clusters are connected by a vast cosmic web of filaments and voids, creating a complex and interconnected structure on the largest scales. The study of galaxies and their evolution provides crucial insights into the history and structure of the universe as a whole. Section 9. Debunking the myths. It wasn't a bang. The Big Bang Theory is often misunderstood. One common misconception is that the Big Bang was an explosion that happened at a specific location in space. However, the Big Bang was not an explosion in space but rather an expansion of space itself. It happened everywhere at once. Another misconception is that the Big Bang Theory explains the origin of the universe. While the Big Bang Theory describes the early evolution of the universe, it doesn't explain what caused the expansion or what came before it. The Big Bang Theory is a scientific theory, which means it's supported by a vast body of observational evidence and is constantly being tested and refined. It's important to remember that scientific theories are not guesses or hunches. They are the best explanations we have for how the natural world works, based on the available evidence. Section 10. The universe today. Still expanding, still evolving. The universe is not static, it's constantly expanding and evolving. The galaxies we observe are moving farther apart from each other, and new stars are being born in galaxies across the cosmos. At the same time, stars are dying, ending their lives as white dwarfs, neutron stars, or black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are formed when massive stars collapse at the end of their lives. Black holes play a significant role in the evolution of galaxies, influencing the orbits of stars and the growth of supermassive black holes at the centers of galaxies. The universe is a dynamic and ever-changing place full of wonder and mystery. As we continue to explore the cosmos, we are sure to make new discoveries that challenge our understanding and inspire us to learn more. Section 11. Keep exploring the cosmos. Our journey through the Big Bang has taken us from the tiniest particles to the largest structures in the universe. We've explored the evidence supporting the Big Bang Theory, from the cosmic microwave background to the redshift of distant galaxies. The universe is a vast and awe-inspiring place. It's filled with billions of galaxies, each containing billions of stars. The sheer scale of the universe can be overwhelming, but it's also incredibly humbling. We are a part of this universe, connected to it in ways we are only beginning to understand. By studying the universe and its origins, we gain a deeper appreciation for our place in the cosmos. So the next time you look up at the night sky, take a moment to contemplate the wonders of the Big Bang. Think about the incredible journey the universe has taken, from a tiny dense point to the vast and complex cosmos we see today. Keep asking questions, keep exploring, and never lose your sense of wonder. The universe is full of secrets waiting to be discovered.